One of the central problems in number theory is to solve Diophantine equations. Recall, a Diophantine equation is an equation where you want to find all integer solutions. You're not interested in other real number solutions or complex solutions. You're only interested in finding those integers that are solution to the equations. Turns out that this is a much more difficult problem than just solving an equation generally. So while in algebra, you're interested in finding all solutions to an equation, in number theory, you're interested in finding particular solutions, and this additional restriction makes the problem more difficult. So we're going to start simply, and in an earlier video, we saw how to solve Diophantine equations with a single variable. We're now going to take the next step in complexity and look at a Diophantine equation with two unknowns. And to keep things as simple as possible, we're only going to look at equations with two variables of degree 1. And before we give a general method for solving these types of Diophantine equations, we're going to look at a particular case which is an important stepping stone to the general solution. So suppose that a and b are integers. Mathematically, you write this as a is an element of z, which is the mathematical symbol for the set of integers, and b is an element of the integers. Then the Diophantine equation ax plus by equals the GCD of a and b has a solution. In fact, it has an infinite number of solutions, but what we're going to do here is learn how to find one solution. And then in later videos, we'll learn how to find all the solutions and then generalize this to any linear Diophantine equation in two variables. So for example, we're going to find a solution to the Diophantine equation 47x plus 30y equals 1. 47 and 30 are relatively prime, so their greatest common divisor is 1. So according to our statement, this should have a solution. Let's see how to find it. The strategy is to use the Euclidean algorithm. And in terms of notation, remember, if you divide an integer a by an integer b, you get a quotient q and a remainder r. And these four numbers are expressed as a is equal to b times q plus r. And we're going to use this notation because it's more compact than the traditional long division notation. So we're going to begin by dividing the larger number 47 by the smaller integer 30. And then we're just going to perform the Euclidean algorithm. So if we divide 47 by 30, we get a quotient of 1 and a remainder of 17. So the next step, we take 30 and divide it by the previous remainder, 17. We get a quotient of 1 and a remainder of 13. The next step, we divide 17 by 13. We get a quotient of 1 and a remainder of 4. And then finally, if we divide 13 by 4, we get a quotient of 3 and a remainder of 1. At this point, we stop because we arrived at the greatest common divisor, so the Euclidean algorithm is over. Now we're going to use these four equations to find a solution to the original Diophantine equation. So first, this will help us use this method. We're going to solve all those four equations, all those four division equations for the remainder. So the first one, we have 47 is equal to 30 times 1 plus 17. If we solve for the remainder, we get 17 equals 47 times 1 plus 30 times negative 1. Rather than write it more simply as 47 minus 30, we're going to be putting these numbers in parentheses because the numbers in parentheses are going to eventually build into the solution to the equation. So this is part of the bookkeeping. Next equation, we have 30 is equal to 17 times 1 plus 13. If you solve for the remainder, and remember to add a number in parentheses, we get 13 is equal to 30 times 1 plus 17 times negative 1. Next, 17 is equal to 13 times 1 plus 4. Solve for the remainder, and that gives us 4 is equal to 17 times 1 plus 13 times negative 1. And lastly, we have 13 is equal to 4 times 3 plus 1. Solving for the remainder, we get 1 is equal to 13 times 1 plus 4 times negative 3. So now what we're going to do is we're going to take this last remainder equation. 1 is equal to 13 times 1 plus 4 times negative 3, and we're going to backward substitute until we get to the very first remainder. And when we do that, this method will terminate and we'll end up with a solution to the original Diophantine equation. Let's see this. So in this remainder equation, we have the integer 4. We have the remainder 4. But in the equation above, in the remainder equation above, we have 4 written as an expression of 17 and 13. So we're going to substitute that in. That gives us 13 times 1 plus, let's substitute that expression in for 4. That gives us 17 times 1 plus 13 times negative 1, all of that times negative 3. Now here we need to distribute through the negative 3, and we're going to take care to multiply negative 3 by the numbers in parentheses, because those are the solutions. So we do this and we get 13 times 1 plus 17 times negative 3 plus 13 times 3. Now combine like terms and we get 13 times 4 plus 17 times negative 3. So we've eliminated 4 and we're now left with just 13 and 17. Now look at our remainder equations, and if we go up one more, we now have 13 written in terms of 30 and 17. So we're going to substitute that in for 13. And we do that, and we get 30 times 1 plus 17 times negative 1, all of that times 4, plus 17 times negative 3. Once again, distribute the 4 and take care to multiply the numbers in parentheses by 4, not the 30 and 17 themselves. That gives us 30 times 4 plus 17 times negative 4 plus 17 times negative 3. Combining like terms, and we have 30 times 4 plus 17 times negative 7. And we can do one last substitution, because we now only have 30 and 17, and if you look at our remainder equations above, you see we have 17 written in terms of 47 and 30, our original coefficients from the equation, so we're almost there. So we substitute this in for 17, and that gives us 30 times 4, plus the quantity of 47 times 1, plus 30 times negative 1, all of that times negative 7. Once again, distribute and combine like terms. Distributing gives us 30 times 4, plus 47 times negative 7, plus 30 times 7. And combining like terms, we have 30 times 11, plus 47 times negative 7. And now we see we have 1, which is the greatest common divisor on the left-hand side, as is equal to 30 times 11 plus 47 times negative 7. So we've now solved the original Diophantine equation. We found a solution. We didn't find all of the solutions, but we did find one. In later lessons, we'll see how we can use this one solution to generate all of them. So the equation 47x plus 30y equals 1 has a solution. In fact, it has an infinite number of solutions, but it definitely has one solution, and that solution is x equals negative 7 and y equals 11. Now this was a somewhat tedious process, but it's important to see it and understand it at least once. Once you've done this, if you're going to solve these type of problems repeatedly, there are several different algorithms out there where they kind of introduce matrix-like objects to help you with the bookkeeping of these numbers, and it allows you to streamline this process so you can very quickly arrive at a solution. Alternatively, you can also just write a computer program to take the A, B, and C from your Diophantine equation and generate a solution for you using the Euclidean algorithm and then reversing it. But once you see this, that you can take the Euclidean algorithm and reverse the process and arrive at a solution to ax plus by is equal to the greatest common divisor of a and b. Next, we're going to use this fact to find a systematic way to find all solutions to this Diophantine equation. Here we just found one, but we want to find all of them, and there's an infinite number of solutions. Stay tuned.